In this video, the goal of what we're going to do is we are going to ask the question, how do we break a vector down into its components when that vector is not drawn in the first quadrant? So the vector could either be directed in the second, third, or fourth quadrant. So as an example, let's just draw a vector. I'm going to call this vector A. So here is vector A, and we are asking what are the components of vector A? In other words, what is a x equal to? What is a y equal to? Let's suppose this vector has a total magnitude just a. A I will write without the arrow. So the magnitude of this vector is a. Magnitude of vector A with the arrow hat is just written as A without the hat. Now, if I look at this vector, we said we could think of the components of a vector as the projection of that vector onto the x and the y axes respectively. So if I draw that out, vector A would project down onto the x-axis. And so the projection of vector A would be right here, which is my AX. And the projection of vector A to the right onto the y-axis would be my AY. Now, just looking at where these pictures have been drawn, I could see AY is going to be a positive number because AY is above y equals 0, but AX is going to be a negative number because AX is to the left of x equals 0. So right away, I can see AX is less than 0, but AY is going to be greater than 0. So what is one method for actually determining the components AX and AY? So the first method I'm going to give you, I will give you what the method is, and then I'll take a moment to justify my claim. Let us say that if I were to begin at the positive x-axis and I begin sweeping in a counterclockwise direction until I reach vector A, I'm going to call this angle phi. I don't know what phi is, but I could clearly see that phi is going to be some angle greater than 90 degrees. So angle phi is going to be greater than 90 degrees. And angle phi, we said, we begin along the positive x-axis and then we sweep until we hit vector A. So begin along the positive x-axis and sweep counterclockwise until you reach your vector. This is important. You begin pointing to the right. You begin along the positive x-axis and then you sweep. And when you do this, you will sweep more than 90 degrees. If you're down here, you're going to sweep around more than 180 degrees. If you're in the fourth quadrant, you will sweep more than 270 degrees. That is okay. Angles could go more than 90 degrees. There is nothing wrong with that. So the component AX is equal to the magnitude of vector A cosine of phi, and the component AY is equal to the magnitude of vector A sine of phi. Where here, phi is this angle bigger than 90 that we had to sweep, and capital A is the magnitude of A. Okay, this is the result. Usually in this course, when we need to break a vector into its components, This method is going to be the easier method to work with. I gave you the result. What is the justification for this result? To see this result, think about in high school when you learned about the unit circle. So let's draw the unit circle out. So we will say this is AX, and we said AX equals A cos theta. AY equals A sine theta. Oh, phi, I mean. Okay, what was the unit circle when you learned about it? Well, we could say here is X, here is Y. The unit circle is a circle of radius 1. So here's a circle of radius equal to 1. Unit circle, radius equal 1. And pick any point on the unit circle you want. So you could pick a point right here. Now, if I draw a line from the center of this circle out to this point, this line will make some angle with the x-axis. Let's say this angle is 42 degrees. I don't know what it is. It seems it's about 42 degrees. Well, we then learned that the x and the y coordinate of this point on the unit circle is x equals cos 42, y equals sine 42. That is the x and the y coordinate of this point on the unit circle. What if we choose a different point on the unit circle? So if I say here is my x and my y axis, what if I choose a point down here? I could begin again pointing along the x-axis, and I could draw a line to this point that I am interested in. This angle is much bigger. This angle is 90, 180, let's say 30 more. So 180 plus 30 is 210. So this angle here I drew is 210 degrees. The xy coordinate of this point on the unit circle is cos 210, sine 210. Okay, now every point on the unit circle could be thought of as defining the angle on a unit circle. A point right here could be given by this angle. A point right here could be given by this angle, and so on. Every point on the unit circle is some angle on the unit circle. So every point on the unit circle has coordinates cosine of the angle, sine of the angle, assuming we begin along the positive x-axis and we sweep until we're pointing at that point that we're interested in. How do we go from this picture to that picture? Well, let's pretend instead of a unit circle, let's look at the unit circle for a moment. Unit circle has a radius 1. We'll take this picture right here. So if I look at this more closely, I could say the circle has a radius 1. If I were to make a triangle up to this point, this angle is my 42 degree angle. This is the point in question. And if I say this is the x coordinate of the point, and this is the y coordinate of the point, I could look at this, I could use what I know from trigonometry and say cosine of 42 is equal to adjacent over hypotenuse, x over 1, which is equal to x, and sine of 42 is equal to opposite over hypotenuse, so that's y over 1, which is just equal to y. So this is why we were able to say for this point here, x is the cosine of 42, y is the sine of 42. What if instead of the unit circle, I look at the exact same thing except I consider a larger circle? Let's pretend I have a circle of radius 4. So now the circle of radius 4 will be something like this. So here's my x-axis, here's my y-axis. It's just like the unit circle, but I made it bigger. And we want to ask, what is the x and the y coordinate of this point? So here is a line drawn from the center of the circle out to that point. And let's say this angle is, I don't know, let's say it's 50 degrees now. So I could look at this and I could say, well, we'll break it down into a right triangle. So this will be the x coordinate of this point, and this vertical part will be the y coordinate of this point. And we did say beforehand that the radius of this circle is 4. That would be the hypotenuse of this triangle. So I could look at this picture. I remember my trigonometry, so I could say cosine of 50 is equal to x over 4, adjacent over hypotenuse. So I get x is equal to 4 cos 50. And y is equal to 4 sine 50 by a very similar line of reasoning. Now at this point, look at what we did here and compare it to what we wrote here in general. The magnitude of the vector is kind of like the radius of the circle. As long as we begin aligned with the x-axis, we could just sweep out to whatever point we're considering, and then say that is the angle, and the x and the y coordinate are given by cosine and sine respectively. And this will hold true for any circle. We can make the circle bigger or smaller. And so if I take a circle of just any radius in general, I'll call it a circle of radius r. So here is my circle of radius r. R could be any number at all. Here's a circle of radius r. Well, this point right here has coordinate x and y. And so if I were to begin and sweep around, and let's call this angle theta, I could say if r equals 1, then the point has coordinates x equals cos theta, y equals sine theta. Now, if r is not equal to 1, because again, if r equals 1, we're just back at the unit circle that we talked about at the beginning of this justification. If r is not equal to 1, we'll remove that restriction. Then the point will have coordinates x equals r cos theta, and y equals r sine theta. It's just like the unit circle that we showed previously with a radius of 4, but now we could stretch the circle out or compress it, make it bigger, small at will. Similarly, I could look at this and I could kind of think of this as an x coordinate. I could kind of think of this as a y coordinate. So this is a justification for why this is the correct way to break a vector down into its components. You don't need to actually be able to formally prove why this justification works in this course, but as I say a lot of times, it's important to me that you believe what I say because it is natural. So I want to back up what my claim with a demonstration of this. Now, I told you there is a second way that you could find the components of a vector that is not in the first quadrant. So I just want to stop right now and say, if you are happy with this method, and if you never use the second method for this semester or next, that's totally acceptable. You may do it. In almost every problem, this method will be the easier problem. Just remember, you must begin aligned with the positive x-axis and you sweep around until you're aligned with the vector. So this angle could be bigger than 90 degrees. The other method, though, in cases of an inclined plane or something on a ramp, in those cases, this other method is often going to be a little bit easier to work with than what we did here. Although for almost every other scenario, this is the easier method to work with. So what I'm going to do is I am going to erase this, and I'm going to erase this angle as well. So let's redraw this picture, and let's say this angle right here, I'm going to call this angle, I don't know, I'll call it gamma. I'm giving it Greek letter gamma. It's kind of like that, I don't know, whatever you want to call that shape. So this is angle Greek letter gamma. Now what I'm going to do to determine the components of A is, the first thing I'm going to do is I'm going to redraw this, look for a right triangle and redraw this picture. So I look at this picture and I notice there is a right triangle here. So I'm going to draw that right triangle. Here is that same right triangle. And this here is the right angle. Here is the hypotenuse with magnitude A. Here is this angle gamma that I drew there. And then I also look at this triangle and I notice this distance is, I'm going to say related to AY. I'm going to say this distance is related to AX. I'll explain why I'm saying related to in a moment. So I'll just call it lowercase ay, lowercase ax. Okay, now I could use what I know about trigonometry, and I could say, okay, well, here's gamma. This is the opposite side. This is the adjacent side. So let's use our trigonometry. Cosine of gamma is equal to a lowercase ay over a. Sine of gamma is equal to lowercase ax over a. Now I could rearrange these terms, so I could say this term will imply lowercase ay equals a cosine gamma, lowercase ax equals a sine gamma. Okay, now why did I say this is related to ax? Why did I not just say this is ax? Well, let's look at how we drew this picture. Very clearly, gamma is some angle between 0 and 90. So clearly, gamma is something between 0 and 90 degrees. What is gamma exactly? It's not important for the purpose of this discussion. If gamma is between 0 and 90, ax and ay, when I'm determining them with the calculation, ax and ay will always be a positive number. So ay, I'm going to put gamma in a calculator. I'm going to take the cosine or sine of it. And when I take the sine or cosine of gamma, I'll get a positive number out. The magnitude of a vector is always going to be a positive number. Capital A is going to be greater than 0. Cosine and sine of gamma will be greater than 0. So when I plug these numbers in a calculator, lowercase ay and lowercase ax will always be a positive number. I'm multiplying positive by positive, gives me positive. So ax and ay will always be a positive number. Notice lowercase ax is greater than 0 and lowercase ay is greater than 0. We did not make any mistake in our calculation. So everything I did is okay up to this point. But now what I have to do is I have to go back to my original picture. My original picture, I have, this is my vector A, So here is my vector A. And I look at A and I then have to step back and ask, do I expect AY to be positive or negative? Do I expect AX to be positive or negative? So I look at this picture and I say, I expect AX to be a negative number and AY to be a positive number. But when I compare this picture with AX, AY, and A, and I have AX is AX is a sine gamma, and AY is a cos gamma. These numbers are both bigger than 0. I know the magnitude, the absolute value of AX and AY will be the same as the absolute value of the component of vector A and this component vector A, but the signs, positive or negative sign, I need to place by hand. So the absolute value of AX will be the same as the absolute value of the component AX that I really want to know. But I need to then say AX is equal to negative A. I need to put this negative sign in by hand. And so I write that as negative A sine gamma. Now I look at AY. I see AY. I know the component of AY will be the same size, the same absolute value as lowercase AY over here. Here AY is positive. Here I expect AY to be positive as well. So I say just AY is equal to AY, which is a cos gamma. So I go through, I find the magnitude of these lowercase AX and AY. The magnitude or the absolute value will be the same as the absolute value of these components, which is what I really want to find. But then I need to look at the picture and I need to place a positive or negative sign in here by hand at the end of the day. So in my opinion, the first method is usually going to be easier. When we are working with problems with an inclined plane, I think this method is a little bit easier. Both methods are absolutely correct. So be comfortable with the method and it'll be just fine. You could always use either. As long as what you do is correct, then everything will be good. So we are given the example problem. We have a vector Q that is a magnitude of 25 and directed at an angle 70 degrees below the positive x-axis. What are the horizontal and vertical components of Q? So here is the positive x and y axis. Q is 70 degrees below the positive x-axis. Here's positive x-axis. 70 degrees below is going to be a pretty extreme angle downward. So 70 degrees below will look something like this. So I wrote my vector Q, and we are asked to find the components Qx and Qy. The horizontal component, which I will call Qx, I will draw on this picture and label Qx. The vertical component, I will draw like so and label it Q subscript y. Now, in my opinion, the first method I'm going to demonstrate for finding these components Qx and Qy is the easy method. We were told that this vector Q has a magnitude of 25. So what are Qx and Qy? Well, we said that I could say Qx is equal to the the magnitude of the vector, which is 25, times the cosine of an angle, and QY is equal to the magnitude of the vector times the sine of an angle. So the only question we need to answer is, what angle do we plug in here and here? And it will be the same angle in both cases. So the way we find that angle is we pretend that we are initially pointing along the positive x-axis, and then we spin around, we rotate until we align with the vector. And whatever angle we spin around or rotate around, that is the angle that we must plug in here and here. It is very possible this angle will be greater than 90 degrees. So we always want to spin counterclockwise. So in this case, I would spin upward. I made an angle of 90 degrees. I continue, I'm at 180. I continue, right now I'm at an angle of 270. 90 plus 90 plus 90 is 270. And then I have to make an angle that's a little bit more than 270. Now, how much more than 270? If I look at the x-axis and the y-axis, I know this has to be 90 degrees. So if this is 70 degrees from here to here, this remaining angle must be 20 degrees. So this will be 20 degrees. And at this point, I could say 90 plus 90 plus 90 plus 20. That's going to be 270 plus 20. That's going to be 290. So the cosine of 290 and the sine of 290. Now at this point, I just get out my calculator and I find Qx is equal to 8.6 and Qy is equal to negative 23.5. At this point, I am completely done with the problem. There's nothing more to do and full marks. If you are curious about what the other method looks like, I'm going to demonstrate that now. On an exam or a homework, you only need to use one method, so I will say use whatever method you are more comfortable with. In my opinion, I think this method is the easier one to work with, but there are some people who feel the other way. So to demonstrate the other method, what we're going to do is I'm going to redraw this vector. So I have redrawn the vector, and what I'm going to do is I am not really going to worry about positive versus negative components off the bat. I'm just going to look for a right triangle. And I look at this vector and I say, yeah, there is a right triangle. This right triangle will be something like this. Now we know the magnitude of this vector q is 25. So at this point, the diagram looks kind of busy, so I'm going to redraw this triangle. So here is this triangle. This is my 70-degree angle. This side I will just call, I don't know, I'm going to call it side A. This side I'll call side B, and the hypotenuse is 25. My goal, what I'm trying to do is I am trying to find what are A and B. So I notice B is opposite of 70, so I could say sine of 70 is equal to B over 25. And then I multiply both sides by 25, so I get B is equal to 25 sine 70, and then I get B is equal to 23.5. And I look at this diagram and I notice A is the adjacent side, the side next to the angle. So I could say cosine of 70 is equal to A over 25. And then I rearrange it, I get A is equal to 25 cosine 70. And I find A is equal to 8.6. Now, if I compare this drawing of this triangle to the drawing over here, the magnitude, the absolute size of A will be the same size as QX, and the size of B will be the same as the size of QY. So the absolute value of QY will be the same as the absolute value of B. But what I do next is, I know QX will have a total magnitude of 8.6. QY will have a total magnitude of 23.5. Another way of thinking that is an absolute value. But I now need to look at this vector. The vector Q is pointing downward into the fourth quadrant. And so I look at this and I say, this vector Q, I expect the horizontal component to be a positive number because it's in the positive side of the x-axis. I expect QY to be negative because Q is overall pointing downward, not upward. So I expect QX to be greater than 0, QY to be less than 0. And so the size of QX is this 8.6. So I could say QX is equal to 8.6 and QY is equal to negative 23.5. And at this point I am done. So I found the size of the components. A and B are the size of the components, and then I need to look at the vector and determine, should I expect the component to be positive or negative, and I then put in a negative sign by hand if necessary. So I'm going to show a third method we can use to find the components of this vector Q. This third method, in my opinion, is not really different from the first method. It's kind of similar, but fundamentally it's the same method. It's just how we're thinking about angles. Now, up until this point, I said if you are using the first method, you begin aligned, pointing along the positive x-axis, and you must rotate counterclockwise until you reach your vector and are aligned with your vector. So when we did that, we rotated counterclockwise, and we rotated counterclockwise, and we said this angle is 290 degrees. So I said QX is equal to 25 cosine 290, and we got 8.6. There is, technically speaking, another way we could have addressed our angle right here. Think about a number line. So if I draw a number line, if I'm moving to the right, that's a positive number. Therefore, if I'm moving to the left, that is where my numbers are becoming more and more negative. Let's assume we start at 0. So positive numbers are moving to, when I move to the right, I move to positive numbers. When I move to the left, I move towards the negative numbers. Similarly, I could think about that in terms of angles. We're going to talk more about the notion of positive negative angles in chapter 8 at the end of this course. But basically, if a counterclockwise rotation is a positive angle, then a clockwise rotation is a negative angle. So just the same, I could, if I want to, begin pointing along the x-axis, and if I rotate in a clockwise direction downward, like this, I would say this is a negative angle. So in this case, this angle would be negative 70 degrees. And if you want to, you could check, you could write QX is equal to 25 cosine of negative 70. And if you plug this in a calculator, you hit enter, you again will get 8.6. And similarly, you could write QY is equal to 25 sine of negative 70. And when you do that, you will get negative 23.5. So, in my opinion, strictly speaking, it's easier just to remember one thing. So I would say you begin pointing along the x-axis, and then you just rotate counterclockwise until you align with your vector. But if you want, you also are allowed to rotate clockwise, as long as you remember clockwise rotation is a negative angle, counterclockwise rotation is a positive angle. So this is a clockwise rotation is a negative angle.